Thank you. Thank you for the introduction and for the invitation to organizers. So indeed, I will talk about some limit theorems for representations of Gromov-hyperbolic groups. Well, I didn't write it, but I will erase it when time comes. There's an announcement. Good. So this is a joint work with Stephen Cantrell, who is a postdoc in University of Chicago. He will soon move to University of Warwick. And okay, so let's start. I will basically start with a theory of random matrix products that will serve as a motivation. So, well, if you, yeah, so don't worry if it's basically motivation. Okay, so in all talks, G will be the group of matrices GLDR or SLDR. Okay, so I will write mu a probability measure. Sorry, probability measure on G. And as we saw several times, a probability measure on a group induces a random walk on the group. So you take xi's, IID random variables. So IID random variables distributed according to a probability measure mu. And then you take their products. So ln, I will write xn, x1. This is the random walk on the group G. And in this context, we refer to it as random matrix products. So random matrix products. So this is not to be confused with random matrices. Maybe it's better to say random products of matrices. These are not the random matrices, but in a different sense of the popular topic. Okay, so the goal of this theory is to describe asymptotic. So this is a generalization of classical standard results in probability theory. If d is equal to 1, you are taking products of numbers up to taking logarithm. You are analyzing sums of random variables. It's topic of classical probability theory. And here in higher dimension, these are still a bunch of numbers, but there's non-commutativity and there's non-subadditivity somehow. And the goal of this theory is to understand asymptotics of random matrix products. And actually, probably Richard was right that one of the first results in general in random walks on groups was due to case 10, 59. But already in 54, there was work of Bellman, who were studying random walks on random matrix products before general result of case 10. But okay, so one of the first results in this business was due to Furstenberg and case 10. This is 1960, just before case 10's thesis. They basically proved this non-commutative law of large numbers. So what they showed is that under a moment assumption, I will not specify it. It's the first moment, the natural one. Assumption. So there exists a constant lambda in R such that 1 over n log, if you take the ln, this converges almost surely to lambda. Okay. So ln is this product. I take, because it's a multiplication, I take logarithm and 1 over n. And this constant, of course, does not depend on the choice of the norm, because it will be killed by the logarithm. It's called the top Lyapunov exponent of this random walk. And this is a law of large number in this setting. It's a generalization of large numbers. Well, it now follows from Kingman's also subadditive ergodic theorem, which was, in fact, which came after Furstenberg-Kesten's theorem, and which was motivated by it. In the same way as law of large number is the particular case of Birkhoff's ergodic theorem, this is a particular case of Kingman's ergodic theorem. And this theory has then been studied for, well, it is still being studied. And we already saw it has relations to stationary measures, fractal objects that we saw in, for example, Joseph Meyer's talk. And then more refined limit theorems are still being studied, and it has been studied since then. So, but some breakthrough results were, for example, more refined theorems. Theorems such as central limit theorem or large deviations or local limit theorems and so on are has been studied throughout. And some of the breakthrough was, for example, given by Lepage in 80s and more recently by Benoit Kahn. I will say what they do in 2010s, which kind of find some optimal assumptions. But to state them, let me introduce some definitions. So So when you have a semigroup or a group inside GLDR, some definitions, these classical things, we say that it is irreducible if there is no proper non-trivial invariant subspace. Okay, so irreducible if there exists no gamma invariant proper non-trivial subspace of RD. You say it is strongly reducible if there is no finite union of such things, no gamma invariant finite union. Okay, so an example is if you have matrices of this sort, alpha, alpha minus 1, and then, for example, 1 minus 1. If you take the group they generate, they will be irreducible, in fact. They will not preserve any subspace, but they will preserve the union of two spaces. So they will not be strongly reducible. And there's also a notion of proximal. This is something proximal. You say that gamma is proximal if there exists gamma in gamma, which has a unique eigenvalue of maximal modulus. So there exists if unique eigenvalue, which is simple, of maximal modulus. Okay, you can keep them in mind. These can be a priori hard to check, but there are very good criterion by Goldscheid and Margulis. For example, if this group is dense in the Zariski topology, in some algebraic topology, all these conditions are automatically satisfied. So in practice, they are easy to check. And so the results of Lepage and Benoit Kahn say, random matrix products. Maybe let me erase this announcement. Well, it sticks. So, for example, theorem. This is Lepage, 82. It says that if you take your mu, is as usual probability on GLD, and you write gamma mu is the semigroup generated by the support. Okay? The semigroup generated by the support. So for example, you take two matrices and you take all their products, and suppose this is a strongly reducible and proximal. Okay? IP. So there's a hypothesis not on the measure itself, but only on the semigroup generated by on the measure of the semigroup generated by the support of the measure. And then Lepage says that, in fact, this result of Furstenberg and Kesten can be made quantitative in the sense that the errors are exponentially small. So probability for every epsilon, probability of logarithm of ln minus n, or n minus lambda bigger than epsilon is, well, there exists, say, for every epsilon there exists alpha, such that this is a of E and alpha. Okay? So the probability of, so I know that this will converge to this number, but then if I fix an epsilon, the errors are exponentially small. And there is also central limit theorem, which is, so this is under an exponential moment assumption, but I won't assumption. And there is a result again due to Lepage, but also the optimal form is due to Benoit Kahn, 2016, under L2 moment assumption, which is optimal. They say that, well, there is a central limit theorem, so logarithm of, so if you write log ln minus n times lambda divided by square root of n, it converges to, in distribution, to a non-degenerate central limit theorem. So these errors are also distributed according to Gaussian distribution. Okay, so I won't go much into detail, but there are many more results and more and more refined. There's various scenes and so on. But what I want to say is that if you look at these results from the perspective of geometric group theory, there's something there's something going on, like, okay, so a typical example I should have given is that, for example, you want to consider a measure like 1/4, maybe Dirac 1, 3, 1, 0 plus minus 1 plus 1/4 Dirac 1, 3, 1, 0 plus minus 1. So I can, a typical example of a probability measure, I can take products of these matrices, right? And so all these theorems applies to this measure, okay? So all the moment assumptions are satisfied, this is finitely supported. The group generated by them is acting strongly reducibly, proximally, and so on. And but from the perspective of geometric group theory, you can distinguish. So there's a products of matrices going on. These are, you do products of bunch of numbers, but also there is something else. There's an abstract group of matrices. Actually, you are doing a random walk on an abstract Cayley graph, and then these points of Cayley graph correspond to some matrices, and then all these theorems say something about the corresponding matrices. Somehow all these are somehow blind to what's going on in the Cayley graph. So you have, in this case, you have a free group, right? So you have they generate a free group, and then there is a representation into this goes into some GLD, if I even SL, right? SL2. And you do some random walk here. In fact, well, you do some random walk. And then you look, these random walk correspond to a bunch of matrices. And then all these results say something about asymptotic behavior of these matrices. And okay, so, but, well, let's say you want to ask the question, what does this say about this embedding of the Cayley graph into GLDR? So you want to say something like, oh, I know that here, if I do a random walk, there is a drift, meaning that the random walk at the end step will be approximately at certain distance. And here I know that it will be approximately at certain growth as numbers, which is written there. Does this mean that the random matrix products tell me somehow a generic element of the Cayley graph, how big it is, or what's this metric properties, or let's say statistical metric properties of this embedding? You can ask this question, and from the theory of, from the perspective of geometric group theory. And when you ask this question, Givash will come and tell you that I have an inequality. So there's something called this fundamental inequality. So this is a growth rate of the group. This is the exponential growth rate of the balls. So no probability on this side. This is the Aves entropy. Aves we solve also in Richard's talk. And this is the drift of the random walk. So these two notions are associated to your measure on the Cayley graph. This is the growth of the Cayley graph. So no measure here. And there's always this inequality. It's quite fundamental. It's quite simple. And Givash will tell you that if this inequality is strict, okay, if this is strict, then in fact the random matrix product theory will not see typical elements of the Cayley graph. What do I mean by that is that if H mu over L mu is strictly less than the growth, okay, then what is happening is that the random walk here, at the end step, it's mostly concentrated on some circular region like this. But in fact, the meaning of this strict inequality means that random walk only sees some exponentially small part of this thing. Okay, so most of your mass is concentrated on exponentially small part of the Cayley graph. Okay? So in this sense, when you apply this result, what they say to you about growth concerns only this exponentially small piece. And okay, then you might ask, oh, maybe it's always equal, but in fact, there is a result of Guezel, Mokuran, Mateus, Mokuran. It tells you that basically, except very specific cases, we always have H mu over L mu is strictly less than this. In these specific cases, for example, forces your group to be virtually free and the support of the measure to be also like free and so on. So basically, you in many situations you have this strict inequality, and then random walk is concentrated on exponentially small part. So the statistics given by random matrix product theory is pertinent only to exponentially small part of the Cayley graph. So, okay, now you guess my question. By the way, this is also equivalent to saying that my result of Pierre Mathieu, who is in the other room. You already listened to my talk before. So Mathieu, okay, Blanchard, Mathieu, and H.M. Hysinski. This is also equivalent to saying that the Patterson-Sullivan measure is singular with respect to the harmonic measure. It's also one notion that popped up in Joseph Mayer's talk. And it turns out that most of the time they are singular, and most of the time, therefore, you have this. And so the question that I will ask in view of all this, now you can guess that I will ask the question that if I pick my element from the group, not with respect to a random walk, which will be most of the time in an exponentially small part of the group, if I pick it uniformly random within the ball in the Cayley graph, do I have some, can I describe the asymptotics? Do I have some law of large number? Do I have some limit theorems for this? Okay, so do there exist limit theorems for, let's say, Ln prime, which is distributed accordingly, uniformly distributed in, let's say, Sn. It will denote either the sphere of radius n or ball of radius n. It doesn't make much difference. Ball of radius n in the Cayley graph. Okay, well, S is a generating set in Cayley graph. So this is the question I will ask. And so now I can state the results. Yes.
The converse to biologisme, do you know that there is always some random walk which is more or less uniformly distributed?
Well, you know that if your group is not virtually free, there is no random walk. No. Yeah. Yeah, these are for some finitely support or super exponential moment, but then you might need to go to.
When Julia would prove that you can find a very non-symmetric random walk for which the stationary measure is absolutely continuous to the Patterson-Sullivan and the Patterson-Sullivan a combination of finite units.
But that will not. Yeah, okay, that's true. But that will not suffice to get what I will say. Anyway. Now the question is this one, and the results is that the answer is that we will be able to basically answer these when group is Gromov-hyperbolic, when gamma is Gromov-hyperbolic, and the truth is that when gamma is not Gromov-hyperbolic in a, let's say, not relatively hyperbolic either. Let's say if it's SL3Z, none of the results I will say, I know the answer. Okay, so the first theorem is the following. Actually, this is Cantrell. Yes, 2022. Let's call it weak law of large numbers. So the first theorem is the only theorem that will be more general. Actually, it will be. There will not be any representation inside. It will be a law of large number for a general subadditive function. So let G be a Gromov, gamma be Gromov-hyperbolic group, and S a finite symmetric generating set. Okay, and let phi from gamma to R be a subadditive function. By subadditive, I mean phi of GH is less than equal to phi G plus phi H for every GH. Okay. Well, then, in fact, there is a law of large numbers. Then there exists lambda, which is in fact non-negative, such that if you look at the elements of the sphere of radius n, and you look at for every, there exists lambda, such that for every epsilon, and you look at the g's inside Sn, for which phi of g divided by n, lambda is bigger than epsilon, this goes to 0. So you have some function, and in fact, the theorem says that there exists a number such that if you look at the sphere of radius n, there is a asymptotically negligible part of the sphere, and if you neglect those, most of the other elements, they take value approximately n times lambda plus minus n epsilon. Okay? And so just a remark. No, the phi is arbitrary, but the limit is necessarily non-negative. This is because of symmetry. The symmetric generating set, it forces the limit to be non-negative. So this is nothing fancy. But yeah, phi can be arbitrary. So an example would be that, well, what kind of examples you have for this kind of functions? Maybe gamma act on some metric space, and then you take phi g to be distance g o times o for a fixed point o. Or you can take gamma, a representation inside GLDR. So you associate to gamma matrices, and then you take phi g to be logarithm of the operator norm. You get, so all these are subadditive functions. And actually, we realized that it turned out that there was a 20 years ago, Kaimanovich, Kapovich, and Schupp, they had basically part of the idea of this theorem. They had proven this theorem when gamma is a free group and S is a free generating set. Okay, so when gamma is free and S is free, this result, this is due to Kaimanovich, Kapovich, Schupp. 2000, maybe 4 or 3. Okay. So, all right. So, in the rest of the talk, that will be about representation. So, in the rest of the talk, I will be giving more precise limit theorems, but not for an arbitrary function. I will take my function to be of this form. Okay. So, in the rest. Phi is a log norm of a strongly reducible and proximal representation. Rho from gamma to GLDR. Okay. And I will try to do better than this theorem in different sense. Okay. Any questions? Don't hesitate to interrupt me. Okay, so first theorem, again with Cantrell, we write C and S. That will be the analog of Lepage theorem, which will say that this error is exponential. If you are talking about phi, which comes from the log norm of a strongly reducible and proximal representation. So if, gamma hyperbolic as finite symmetric generating set, and gamma GLD strongly reducible and proximal, then these errors, so for every epsilon, so this is lambda, for every epsilon, 1 over n, Sn, g in Sn, such that logarithm of g, rho of g, divided by n minus lambda divided by epsilon is O E alpha n. Okay, so we just wrote what I said. So you can show some more quantitative law of large number with exponential error in this case. And one other result is you can show central limit theorem actually. So same hypothesis. You can show that, well, you know that on the nth sphere, the average behavior is like n times lambda for the corresponding matrices. So central limit theorem is about looking at fluctuations around the mean with glasses that magnifies with square root of n. And then you also get actually, for this counting problem, you also get a Gaussian limit. And so it says that, maybe let me write this way. There exists a constant C, there exists a sum for all t. In fact, we also get some Berriesian kind of central limit theorem, which has an error rate somehow a bit stronger. So what you do is let me look at my notes. I always forget the normalizations in the Gaussian. So I will look at number of g in Sn such that logarithm of rho of g and minus n lambda divided by square root of n less than t. I will do minus 2 pi square root of n t e to the 2 e to the sigma square to s ds. This is less than c log n and 1/2. So this is basically this tells you that you will converge to Gaussian limit, and this is an error rate. In the standard Berriesian, this is a 1 actually. You don't have a logarithmic thing, but we cannot get rid of this logarithmic error. But anyway, you have some kind of quantitative convergence to Gaussian limit. Okay. So one last theorem I want to state is about this constant lambda in the case of random matrix products. So any questions so far? I'm about to state this. Thanks. I don't need to remember my talk. So, in fact, yeah. So the last theorem is, so you suppose, again, gamma representation, in this time SLDR, because I don't want to deal with the determinant, rho, strongly reducible. Then lambda is strictly positive if and only if rho of gamma is not relatively compact. Compact, in particular, if proximal. If proximal. So as soon as you are strongly reducible, the obvious obstruction is the only obstruction. So just a remark here is that this might be a little bit surprising in the sense that you see there is no discreteness assumption on the representation. So a priori my gamma can be going into SLDR in a dense way. Okay? And this means that if I look at the nth sphere, since let's say if I take a compact, there are infinitely many elements of gamma, there is necessarily elements that doesn't go to infinity, that there are necessarily elements that keep coming back to some compact part. But in fact, these are tiny, they are exponentially small. So except exponentially small elements, most of the norm of most of the elements grow like lambda, which is strictly positive, even if your representation is dense. Because in SLDR, let's say. Okay. And indeed, so this is all about all I wanted to state. There are some more refined. We can do some kind of. We also get some limit theorems like Donskier invariance principle. You can do like you can interpolate these norms and then you normalize and you converge to a Brownian motion and so on. But I won't talk about it. So the last thing I want to talk about is some kind of application or a consequence. Just I want to put into perspective with a result of Raghunathan, Lubotzky, and Mozes. Okay, maybe before this, let me tell you, none of these results I know for SL3Z. Okay. Maybe remark. If you take SL3Z to be gamma, and then you take your favorite generating set, I don't know if there is a law of large number. I know even less, therefore, if there is exponential law of large numbers and central limit theorem and so on. So even for the standard embedding and your favorite generating set. No idea. Okay, one consequence is, so let's look at this Lubotzky Mozes Raghunathan. They say the following thing. So if G is a higher rank semi-simple D group, so think of SLDR if you want D bigger than 2, 3, and gamma is gamma inside G irreducible lattice. Okay, think of SLDZ. Okay, what they say is that in this situation, the Cayley graph is quasi-isometric, in fact, Lipschitz to the natural Riemannian metric here. Okay, so gamma endowed with a Cayley graph is by Lipschitz to G endowed with natural Riemannian metric, which is a left G invariant and by invariant by SOD, for example, coming from Killing form, and which is also you can also say that it is by Lipschitz to the symmetric space. Okay. And the image of this, under the natural image. And one way to state it is following. So if you want, there exists a constant equivalently. Okay? There exists a constant C bigger than 1, such that for every G in the nth sphere in the Cayley graph, if you look at its Riemannian distance to identity, it's between C times n and C times n minus 1. C minus 1 times n. Sorry. Okay? And so this means that you look at the nth sphere, all elements are growing necessarily at least with rate 1 over C, and at most with rate C. Okay? And LMR also notes that this result fails for rank 1. For example, for SL2Z, notes that this fails for SL2Z. For example, if you take these 1 and 1, these matrices, 1 and 0, so in the Riemannian metric, they will be log n, okay, for dr, and they will be n about approximately log n, approximately n for the Cayley metric. So they are not Lipschitz. Okay. But nevertheless, what these results, in fact, with some representation theory, what they imply is that, in fact, statistically, the embedding is even more than by Lipschitz. Statistically, it's more like a homotopy. So this is the last thing I will state and finish with that. Just erase one part. So corollary, let me write there the corollary of this result is that when gamma inside G, this is again semi-simple, this is hyperbolic, okay, and this is a, let's say, okay, let me write Zariski dance, okay. If SLDR, you can take strongly reducible and proximal, if this is SLDR. Zariski dance representation, and then what happens is that for every epsilon, there exists a set B epsilon inside gamma, which has the following property that if you intersect this B epsilon, these are bad elements, with sphere Sn, this is exponentially small. So this is a subset of the gamma. If you intersect with the nth sphere, this is just exponentially small part of the sphere, such that then what? Then for every such that this, and for every n, for every g inside Sn, which is not in this bad set, so which is not in this exponentially small part, we have distance g to identity in the Riemannian distance. This is between lambda plus epsilon n and lambda minus epsilon. Okay, so in some sense, statistically, this is true, and it's more than what is true is more than this, because here you see you are between c, your rate is between c and 1 over c, and here your rate is, if you forget about exponentially small part of these things, your rate is between lambda plus epsilon and lambda minus epsilon. So it's basically like a homotopy embedding. Okay. And but still, this result, I don't know if this version is true for SL3Z again. Okay, that's all I wanted to say.